So what is a common ion effect? It is a suppression of degree of dissociation of the weak electrolyte by adding a strong electrolyte which are having common ion. The salts are of three types. One is soluble salts, sparingly soluble salts and slightly soluble salts. So what is ionic product? It is a product of molar concentration of constituent ion raised to their powers at any solution of an electrolyte. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called equilibrium. Under this unit, we have discussed about what is a buffer solution and types of buffer solution, and also we have solved some of the numerical. Today, let us move on to the next topic of this unit by understanding the common ion effect, solubility of equilibrium of sparingly soluble salts, and solubility product or solubility product constant or solubility product expression, and we are going to understand what is the ionic product, and we are going to solve one of the numerical. Okay. First we will see what is a common ion effect. To understand this concept, I'll take the example of acetic acid. We know that acetic acid is a weak electrolyte which dissociated to give H plus ion and acetate ion. Correct now? Which dissociated to give what? H plus ion as well as with the acetate ion. To this solution, if I add HCl, which is a strong acid, which ionizes to give H plus ion and Cl minus ion. So now what will happen? There is a depression, or we can see that there is a suppression in the dissociation of the acetate ions will be observed. So what is it? It is nothing but a suppression of degree of dissociation of the weak electrolyte by adding small quantity of strong electrolyte having the common ion. Here in this example I have taken out the weak electrolyte which dissociated to give H plus ion and acetate ion. To this weak electrolyte I have added the HCl gas which is a strong electrolyte. So you can see that in these two electrolyte H plus ions are common, correct now? As a result of this, you know, there is a suppressions in the dissociations will be taking place. As a result of this, you know, this will be caused due to the common ion, hence this effect is known as what? Common ion effect. So what is a common ion effect? It is a suppression of degree of dissociation of the weak electrolyte by adding a strong electrolyte which are having common ion. Okay. So example, we can take the acetic acid which undergo partial ionization to give H plus ion as well as with the acetate ion. Now for this equation, if you apply the law of mass action, it tells that the law of mass action, that is a dissociation constant which is obtained by a ratio of the molar concentration of the product divided by molar concentration of the reactant. So here K is equal to molar concentration of the product divided by molar concentration of the reactant I obtained. To the small quantity of sodium acetate which has been added, so the acetic acid ion concentration will be increases. In order to keep the K value constant, you know, the H plus ion should be decreases and acetic acid concentration will be increases. Therefore, the degree of dissociation of the CH3COH will be get suppressed. This is because of the common ion, and it can be suppressed by adding a HCl or any other strong electrolyte containing common ion. So you can take the one more example of CH3COONA. Now we know that CH3COONA which is dissociated to give acetate ion as well as with a sodium ion, correct no? But we have with a weak electrolyte, that is CH3COH, which is dissociated to give H plus ion as well as with the acetate ion. Correct, no? Now if you see these two reactions, the acetate ion concentration will be increased. Now, in order to keep this K value constant, we have to increase the concentration of H plus ion. Okay. So, we need, in order to keep the K value constant, so what you will do here, if you write the equilibrium constant, that is CH3COH plus H divided by CH3COH. This is for this reaction, correct, no? Now, in order to keep this K value constant, either I need to increase the concentration of the acetic acid, or either I should decrease the concentration of the H plus ion. Thereby, the common ions like acetate ion will be get balanced and shows the common ion effect. So, what is the common ion effect? It is nothing but a suppression of a degree of dissociation of the weak electrolyte by adding a strong electrolyte having a common ion. Now, for these two reactions, if you write the law of mass action, K is equal to molar concentration of the product divided by molar concentration of the reactant. Now, in order to keep this K value constant, either I should decrease the H plus ion concentration or the acetic acid concentration less, so that the concentration of the acetic acid will be get increased. This is how we can understand the common ion effect which has been formed by the common ions. Thereby it decreases the degree of dissociation. Next we have the solubility equilibrium of sparingly soluble salts. Every salt has a characteristic solubility and it depends upon the temperature. On this basis, we can classify the types of salts into three types. First one is soluble salt. I can give you the example for this. Now, I'll take the glass of water. To that, I'll add a teaspoon of sugar. If you stir it, we know the sugar will dissolve in water. If you continuously add 3 to 4 spoons of sugar also, it will dissolve in water and it will form a sugar solution. But at particular room temperature, if you add more sugar solute, it does not dissolve in water. So, such solutions are said to be a saturated solution. In that solution, you can see that there is a insolubility of sugar salts will be left behind at the bottom of the solution. So, based on this, you can say that the salts are of three types. One is soluble salts, sparingly soluble salts, and slightly soluble salts. If I say it is a soluble salts, their molarity will be usually lesser than 0.1. If I say it is slightly soluble in the sense, only the small quantity will be soluble in water. It will be ranges from 0.01 molar to 0.1 molar. If I say it is sparingly soluble in the sense, very forcefully we can say. Very forcefully, small amount of solute which has been dissolved in solvent, which is said to be a sparingly soluble solution or salt. Example, and their molarity will be usually greater than 0.01 molar. Now, for such saturated solution, okay, in a saturated solution of a sparingly soluble salt solution containing both the ion and undissolved salt, therefore, there is a equilibrium will be established between both the ion and with the undissolved salt. That is called as what? Solubility equilibrium. What we call for that? Solubility equilibrium. So, I have considered the saturated sparingly soluble salts which we dissolved in water, it forms an ion as well as with a undissolved salt. Between these two, you can say that there is an equilibrium will be established, that is known as what? Solubility equilibrium. Next, we have the solubility product, that is KSP. How to derive an equation for KSP, we will understand now. Consider a saturated solution of sparingly soluble electrolyte AB which contain both ion and undissociated solute. Therefore, the equilibrium will be established between these two. This is my solution which consists of sparingly soluble salt which forms an equilibrium between the ions along with their undissociated solute. Now, if I apply the law of mass action to the above equation, law of mass action tells that it is obtained by the ratio of the product divided by ratio of the reactant. So, K is equal to molar concentration of the product divided by molar concentration of the reactant. Now, I will multiply K with the molar concentration of the AB which is equal to molar concentration of the A into molar concentration of the B. I will call the equilibrium constant K into molar concentration of the AB which is nothing but a KSP which is known as what? Solubility Equilibrium Constant. Solubility product or solubility product constant. So, what is KSB here? KSB is nothing but a solubility product or solubility product constant. How I can define the solubility constant here? The solubility product will be obtained by the product of molar concentration of the ion to the molar concentration of the undissociated ion or undissociated solute molecule, or in terms of reactant, if you say the KSB is nothing but a solubility product will be equal to the product of molar concentration of the product. Okay. So, how we can say the definition? The solubility product will be equal to the product of molar concentration of the constituent ion raised to their appropriate powers in a saturated solution of sparingly soluble electrolyte at given temperature. Here, there is no stoichiometric coefficients are there, hence I have indicated with the bracket. Okay. Next, we have the solubility product of different electrolyte. So, you can see that if my electrolyte is AB2 type, how to write the KSP value? So, we know that for AB2 type, AB2 is my electrolyte which dissociated to give A2 plus 2B minus. So, what is the KSP value I can write for this? So, it is a molar concentration of A plus into molar concentration of the B into raised to the power of 2. Okay. Similarly, for A to B type, KSP value will be molar concentration of the A plus into the stoichiometric quotient 2 and B minus minus. Similarly, for AB3 type, we can write AB3 will be dissociated to give A3 plus B minus, and we need to balance it. So, it is 3B minus. So, KSP values for this reaction is A3 plus into molar concentration of the B minus raised to the power of 3. So, it is A plus into molar concentration of the B minus raised to the power of 3. Similarly, for AB4 type, so how we can write? So, AB4 will be dissociated to give A4 plus B minus, B will be 4. So, KSP values will be A4 plus into molar concentration of the B minus raised to the power of 4. Okay. Similarly, you can write for AB4 and B4, and the KSP value will be A to the power of 4 plus and the whole cube divided by B to the power of 3 minus and a whole 4. Okay. Next, we have solubility product expression. Let us consider again with a saturated solution of sparingly soluble electrolyte AB and the equilibrium established between the ions as well as with the undissociated molecule or with a solute. So, here I have taken out the sparingly soluble solute, okay, which is a saturated solution which is dissociated to give ions along with the undissociated solute. Let now I will consider S will be the solubility of AB in mole per dm cube. So what will happen to the KSP value for the above equation? KSP is equal to molar concentration of the product. So here we have a two product, that is molar concentration of the A plus into molar concentration of the B minus, and I said the solubility of the AB, which I expressed in terms of S, so that S is a solubility of the AB which is dissociated to give what? A plus and B minus. So I'll take S into S, which is nothing but a S square. So the solubility product expression will be equal to S square, and this is a relationship which relates the solubility product along with the solubility. So solubility product will be related to the solubility of the electrolyte, and this is a expression. Okay, so this is the expression which relates the solubility and the solubility product of an electrolyte. So let us write the solubility product expression for the different electrolyte. For AB2 type, the KSP value will be, again I can write AB2 in the sense which dissociated to give A2 plus plus 2B minus. So KSP value for the above equation will be molar concentration of the A2 plus into molar concentration of the B minus raised to the power of 2. So now the KSP for the above equation is S plus 2 into S, which is nothing but a 4S cube. 2 into whole square we have to do. So S into 2S whole square will be equal to 4S cube. Okay. Similarly for A to B type, the KSP value will be A plus square into molar concentration of the B minus. So the concentration of the S will be 2S to the power of 2. So into S, which is equal to 4S cube. The last type is AB3 type. For this, if you write the KSP value, that is the solubility product value, that is A to the power of 3 plus into B to the power of minus raised to the power of 3, which is equal to S into 3S whole cube, which is nothing but a 27S4. Okay, this is how we will write the solubility constant or the solubility product expression. Next we have ionic product. Let us see what is an ionic product. It is a product of molar concentration of the constituent ion raised to their appropriate powers in any solution of electrolyte. So what is ionic product? It is a product of molar concentration of constituent ion raised to their powers at any solution of an electrolyte. So I'll consider the solubility product with the different principles. If IP, that is nothing but ionic product, is lesser than KSP, that is the solubility product expression, then the solution is said to be what? Unsaturated. Therefore, precipitate will be do not takes place. Now I'll take IP value, that is ionic product value, will be equal to the KSP value. Then I can say that the solution is saturated. Therefore, the precipitation will not takes place. I have one more condition. If the IP value is greater than KSP, then the solution is super saturated. Therefore, the precipitations will be taking place. To understand whether the given solution can undergo precipitation or not, I can go with a ionic product. Okay. To solve this numerical, first we need to write the balanced chemical equation for silver chromate, that is Ag2CrO4, which ionizes to give Ag plus CrO4 2 minus. In order to balance this, I'll write 2. Now, in order to calculate the solubility constant for the above equation, which is obtained by the molar concentration of the product. So it is Ag, molar concentration of the Ag into molar concentration of the chromate ion. So raised to the power of 2. So what is the concentration of the Ag they have given? 5.0 into 10 to the power of minus 5 whole square into, for the chromium it is 4.4 into 10 to the power of minus 5. Now if you first square root of this and multiply with this number, you will get 1.1 into 10 to the power of minus 13 mole cube and dm power 9. This is a KSV value, that is a solubility product of the above equation. So hope you all understood with this, a last numerical of this unit. So by this I have completed with the equilibrium units, and please see that while solving the numerical they can ask the twisted question. So before solving that question, write the balanced equation, then solve with the numerical. So hope you all understood with this unit. I'll come back with the next unit. Till that, take care and be safe. Thank you.